Alright, let's take a look at today's lesson. Today we're going to be looking at graphing polynomial functions and zeros of polynomial functions. This we would have covered last year in Algebra 2. We're just kind of highlight some really important things. There may be a couple of things new for this year. So let's just kind of work through that. Alright, so graphing. So what we're going to do to graph a polynomial function, we're going to look at a few things. First of all, we're going to determine the end behavior. And these are the indications of end behavior, which I'll get to in just a moment. So we'll do that first. We look at end behavior. Then we would find the zeros. We're going to find the zeros of the polynomial. Next, we would make a t-chart, including test points that are between the zeros. So what we're doing, for example, here, we want to know what's happening between zeros. We want an estimate of how high or low the graph goes between the zeros, and we'll look at that in an example. And last, we would determine the multiplicity of each zero, and we would match the shape that it's supposed to look like. So let's talk about end behavior. If the degree of the polynomial is odd, for example, the leading coefficient, say 3x cubed plus 2x minus 4. Okay, so my leading term, the degree is odd, it's 3. So if the degree of the polynomial is odd, that is the top two boxes. If the leading coefficient is positive, then the graph is going to end up. It's going to start down and end up. Like this. This leading coefficient would be positive, so the graph would start down and end up. If the leading coefficient were negative, let's say that were a negative 3, then the graph would start up and end down. This is something that we learned last year, and it's really something just kind of to memorize. I don't have a better way to help you with that. It's just to kind of memorize what those graphs are supposed to look like. This notation, as x heads to negative infinity, as x gets smaller and smaller, y gets smaller and smaller. That's talking about the behavior of this side. And as x gets larger and larger, we're going this way, y gets larger and larger. That's talking about the end behavior of this side. So we do need to also be familiar with this kind of notation and be able to answer questions regarding and using that kind of notation. Let's look at the other option. Let's say that our polynomial has an even degree. So, maybe we have, let's see, 3x to the fourth plus 4x cubed plus 2, something like that. So notice how our leading, it's a fourth degree polynomial, and that makes it even, so it would be down in these categories. If the leading coefficient is positive, like this one, then both ends would go up. And if this leading coefficient would be negative, like that, both ends would go down. So, even, they're either both up or both down, depending on the leading coefficient. That last part where we talk about the multiplicity of each zero, that goes to here, what we're talking about for graphing. So let's say that the multiplicity is odd. So let's say, in other words, we have, let's say we factored this, and we notice that we have 3, basically x equals 3 occurs 3 times. This would be a multiplicity of 3. So that's what this is talking about. If the multiplicity is odd, then at 3 we would have this kind of squiggly behavior going on, depending on depending on which kind of function we have would depend on which way we were coming, whether we're coming from the bottom or the top. But right at 3 we would have this kind of squiggly kind of behavior. That happens when the multiplicity of the root or 0 is odd. And if the multiplicity is even, let's say, it looks like this maybe. So notice how x equals 3 now has a multiplicity of 2. Then we would have this kind of behavior called a bounce. Maybe you remember that from last year. We would have like a bounce at 3. If the multiplicity is 1, if there's just one of the root occurs, then it would be the graph, it would look like a cut through. It would just kind of like a line. It would just cut through at that root. So that's the significance of multiplicity when we're graphing. The other concept that we're going to be looking at today, another couple concepts, have to do with zeros. So this really kind of is all the graphing stuff we're going to talk about. Now let's talk about zeros of polynomial functions. We are going to be looking at the rational root theorem today. If you recall, probably you remember this with fond memories, P over Q. That's what we're going to be doing today, the rational root theorem. What the theorem tells us is if that a polynomial has a rational root, now let's remember what rational means. Rational is a class of numbers, right? So our big category is complex numbers. Underneath complex, we have real and imaginary. And under real, we have rational and irrational. Some examples of rational numbers would be 2/3 or 5. Some examples of irrational numbers would be like the square root of 2 or pi. Those would be rational versus irrational numbers. This rational roots theorem only finds this kinds of roots, the rational roots. It does not find irrational or imaginary roots. It is only good for rational roots. So what do we do? Well, the theorem tells us that we can find all the numbers created by this fraction are the only possible rational roots, and then we have to kind of work through the list. It would be factors of the constant term over factors of the leading coefficient. This would be P and that would be Q, and we will look at an example of that in just a moment. The last concept for zeros is called Descartes' rule of signs. This is probably new. I don't know that you really covered this last year. It's kind of a cool thing. It's saying the number of positive real zeros equals the number of variations in sign of the polynomial, or is less than that by an even whole number. So number of variations in sign of the polynomial is talking about like if we have 3x squared plus 2x minus 1. So this is our polynomial. I go from a positive to a positive. That is not a sign variation, is it? There's no sign variation. I go from a positive to a negative. That would count as one sign variation. Okay, so that would be one sign variation. So that means that there's one positive real zero for this equation that this polynomial that I just kind of made up. To do the number of negative real zeros, we would have to find P of x. You know, this would be P of x. We'd have to find P of negative x. So we'd have to put a negative x everywhere there's an x. So in this case, we'd have to do, so it'd be like 3. We'd put a negative x in place of that x. So we would do 3 times negative x squared plus 2 times negative x minus 1. Negative x squared we know is a positive, so that would be 3x squared. And then that would be minus 2x minus 1. And so our sign variations, we go from positive to negative, so that's one sign variation and there's not another. And there would be one negative. Now this or less than that by an even whole number, what that's talking about is it's accounting for the imaginary or irrational zeros that may be there. So for example, let's say we have 5 sign variations. Okay, let's just say we have 5. There are 5 sign variations. That means that we would have 5 zeros, or excuse me, not zeros, 5 positive real zeros, or 3 positive real zeros, or 1 positive real zero. That's what that means by or less than that by an even whole number. Okay, so let's jump into our examples. Let's go to the next page and work some of these problems. Okay, so the first one we're going to graph. We're going to sketch a graph of the polynomial. We're going to follow those guidelines on the first slide. So we look for end behavior first. This is odd, and it's positive. So the end behavior is going to look like this. It's going to end up. So that's the first thing that I check is end behavior. got that. Now we need to find the zeros. So we look at that and we think, well, goodness, hopefully, let's see, we can probably factor that by grouping. Let's try that. So let's see, we have x squared, and that's x plus 3. And we think to ourselves, is there something that we could divide out that would make that last, factor x plus 3? Yeah, what if I did a negative 4, divide that out? I would have x plus 3. Hopefully we remember how to factor by grouping. Then these two things are the same. These factors are the same. So I complete this by factoring the x plus 3 out of both of these terms. And I'm left with x squared minus 4. And from here, I think we can see that we would have a 0 of negative 3 and of plus minus 2. Okay, so we found our zeros. So now let's start graphing. So I need to be sure I go over as far as negative 3. Okay, so we have a 0 at negative 3, we have a 0 at negative 2, and we have a 0 at 2. Alright, so the points that I'm required to find are the points that are between, exactly between the zeros. So let's do a little t-chart over here. I need to know what negative 2.5, I need to know that y value. So let's plug in negative 2.5 in our original problem, and we get 9/8. Then the next two zeros, see these, the exact middle part would be at 0, at an x of 0. And when I plug in that, I get a negative 12. So that gives me some idea about the maximum value and the minimum value in this local area. So that's 9/8, so we'll put a point right there. And then we have negative 12 down here. We'll put a point right there. So our end behavior started down and ended up. So let's do that. We're going to start down and we're going to follow these paths. And we're going to end up. So in finding these points, what we're doing is we're estimating what that local maximum is or that local minimum is. It's just an estimate. Next year in calculus we'll be able to find the exact value, but this time we're just estimating. And that's what we need to do when we are graphing. Okay? Now the next problem asks us to find all real zeros. So we look at that and we think, could we factor by grouping? No, that's not going to work. Okay, we get to do P over Q. Yay, rational root theorem. So P are all of the factors of the constant. So we need to think about all the numbers that multiply to get 4. Let's see, 1 times 4 and 2 times 2. So 1, 2, and 4 are all the factors of P. Q are the factors of the leading coefficient. So we need to think of all the numbers that multiply to get 2, and it just so happens to be just 1 and 2. So now let's find all our possible ones. It's basically P over Q. So I have to take 1 and then match it with each of the items in Q. So 1 over 1 is 1, and then I have 1 over 2. Now I take 2 and do the same thing. 2 over 1 is 2, and 2 over 2 is 1, which I already have, so I don't need to write it again. So now we'll do the 4. 4 over 1 is 4, and 4 over 2 is 2, which we already have. So those are all of our possible rational roots. What that means is we have 8 different numbers to try in our synthetic division. That's exciting, right? 8 whole different numbers. So if you're like me, I'm not that lucky. I usually don't guess right on the first time. I usually have to do several rounds of synthetic division before I can figure out where 0 is. So I have already done this problem, so I'm just going to go straight to, I know one of the zeros is negative 2. So then remember about synthetic division, we copy down those coefficients. If there's a missing one, remember to put a 0 in its place. It's 3, 2, 1, constant. There's no missing one. We bring down the first number, then we multiply. Negative 2 times 2 is negative 4. We add down. Negative 2 times 3 is negative 6. We add down. Negative 2 times negative 2 is 4. We add down. My remainder is 0, therefore I know that that is a root. We're supposed to find all real zeros. So x equals negative 2. That's one of my answers. Now what we do is, since I have gotten down to a quadratic, I'm going to kind of scrap the p over q and just do quadratic techniques. I'm going to translate this into a quadratic. 2x squared plus 3x minus 2. And I'm going to look for the zeros in that. Now, we've got a lot of techniques. We could try factoring. Hopefully it factors. If it doesn't factor, we could do quadratic formula or complete the square. We have several options. I'm going to try to factor. I certainly would prefer to do that. So let's see, our back sign is negative, so our signs have to be different. And it looks like that does work. So this gives me a root of 1/2 and negative 2. Look, we already had a negative 2. So basically what I have is my roots are negative 1/2 and negative 2 with a multiplicity of 2. That's what multiplicity is talking about. I have 2 of those same roots of negative 2. And there is our first encounter this year with p over q. So the last example has to do with Descartes' rule of signs. That's kind of a new concept. I briefly explained it on the last slide when we were looking at the theorem itself. So let's just kind of go through and work through this. We're looking for the number of positive real zeros, we're looking for the number of sign changes. So I go from a positive term to a negative term, that's one sign change. Negative to negative, that's none. Negative to negative, that's none. So my possible positive, or not possible, but actually my positive number of positive real roots. So positive real is 1. I have one positive real root. Now let's check out negative. To do that, I have to find p of negative x in order to check out how many negative roots that I might have. So we would just open up everywhere there's an x and put a negative x there. And then clean it up so we can, tell what's going on. We know negative x cubed is negative x. We know negative x squared is positive, and there's a negative on the outside there, so negative x squared. Then we double negatives gives me a positive. So let's check out what's going on. So I have no sign change here, negative to negative. Negative to positive, that's 1. Positive to negative, that's 1. So possible negative root, or negative real, it's not possible, it's our, let's just write negative, come on. Negative real roots, our possibilities are 2, and an even whole number below that would be 0. Now why didn't I do an even whole number below 1? Because if I do 1 minus 2, I get negative 1, and that doesn't make any sense. We can't have a total negative 1 possible or positive real roots, so that's why that didn't work. Now we are asked to determine the total. So total would be, let's see, I could have 1 positive and 2 negative, so I could have 3 real roots, total real, or I could have 1 positive and 0 negative, and those are my only 2 options. My total real is only going to be simply 3 or 1. Okay, hopefully that is helps. If you need any help, just please feel free to ask me questions.